Everybody for the second talk of this morning session. And it's a great pleasure for me to introduce Nikita Nekrasov from the Simon Center of Geometry and Physics in Stony Brook. So Nikita has made seminal contributions to string theory and gauge theory. He did his PhD in 1996 in Princeton under the supervision of David Gross. Then subsequently he went to Harvard as a Harvard Society Fellow, then returned to Princeton as a Dicke Fellow before becoming a permanent professor at the IHES in 2000. He was at the IHES until in 2013 when he went to the Simon Center to become a professor there. So, as I said, he's made seminal contributions to string theory and gauge theory. In particular, he's famous for the so-called Nekrasov partition function, and that's, in some sense, that's the instanton counting of a certain gauge theory or string theory. But the reason why it's so influential is that it's also had different incarnations or has led to connections with gauge theory and with infinite dimensional representations of infinite dimensional algebra. So it's been a very important partition function that's had has triggered a lot of work in different areas of mathematical physics and string theory. He's also made other important contributions. In particular, he's worked on non-commutative instantons. He has pioneered, together with others, what is now called the beta gauge correspondence, and he has made very important contributions to topological string theory. So it's a great pleasure to have him and a great pleasure to introduce him. And he's going to talk about instantons, and I guess there is a pun in his title, The Count of Instantons. Nikita, the floor is yours.
Thank you very much, Matthias. It's a pleasure to be introduced by my neighbor at Harvard. Thank you very much to the organizers for setting up this conference, especially at these difficult times. And thank you for inviting me to give a talk. So I'll try to share my screen. The test question is, do you see the black box in the middle of the screen?
Yes.
Oh, there is a black box?
No, you mean we see a black box that said the count of instantons?
Oh, no, that's fine. That's a good box. Okay. All right. Okay. Thank you very much. So, I don't know how to get rid of this. But, so I'm going to talk about the count of instantons of all kinds. The other title is Playing with the Building Blocks of the Universe, which is probably more ambitious and more playful. So here are my collaborators and teachers and people who inspired me. I mean, most of the people on this slide I've worked with. Some people I wish I worked with. Some of them, unfortunately, are no longer with us. But all of them taught me something, and they were quite influential in what I'm going to talk about. So let me begin by saying that the world around us is full of emergent structures, from the shapes of lightnings and snowflakes to quantum electron liquids exhibiting fractional Hall effect, the relativistic invariance of electrons propagating in graphene layers. So the relativistic invariance here is the emergent phenomenon, and probably the structure of space-time itself. So classically, space-time is a pseudo-Riemannian manifold described by Einstein equations, but quantum mechanically, space-time might be something completely different. And indeed, in the popular approach to quantized gravity is to approximate space-time by some discrete structure. So at first, it appears that we are just deviating a little bit from the geometry, but then to develop tools for summing over such discrete structures, one discovers a kind of a dual description where, for example, in 2 dimensions, summation over the triangulations, so like discrete geometries, turns out to be most efficiently done using matrix models. So the dual graphs of the triangulation are mapped to 2 Feynman diagrams of an integral over some matrices in the limit when the size of the matrices is large. And so in a way, the quantized two-dimensional geometry becomes an object of a different nature. It becomes a matrix acting in some auxiliary space. And so it becomes an intrinsically quantum object, so that it's not obvious how to ask a geometrical question if you have an element of a sample of this random ensemble of matrix models. So in a way, it's an example of a non-commutative geometry. So in the success story of two-dimensional gravity, where one recovers so that one can organize the sum of the geometries according to the topology, to the genus of the corresponding Riemann surfaces. That expansion in genus corresponds to the expansion in the size of the matrices. So one integrates over matrices of size n by n, and then one, in a sense, one analytically continues the result as a function of the size of the matrix, and the dependence of the size of the matrix is equivalent to the genus expansion of the gravitational story. If we go up in dimension, it turns out that it's hard to generalize this idea. I mean, it's easy to generalize the triangulations, and in some sense, the summation of a two-dimensional discrete geometries by matrices becomes the summation by tensor model, where the basic object is now not a square but a cubic matrix. And so the interaction vertex would correspond to a tetrahedron along which one glues three columns built on top of a triangle. So despite some progress in understanding these models, there is no obvious generalization of the genus expansion, except that recently there was found an analog of a planar limit in a so-called SYK model, which is equivalent to one of these tensor models. This is a so-called Grau index, and so in the analog of the planar limit, the only diagrams of that model which survive are the so-called Mellon diagrams, as opposed to the planar diagrams of the matrix models. Now, it doesn't seem to be possible to generalize it further, and we would like to have at least four-dimensional random geometries, but even about the three-dimensional geometries, there are lots of questions and there's a lot of confusion. So any kind of statistical mechanical model which generates the geometry of dimension higher than 2 might be of interest. So today I'll briefly talk about a class of models which, on the one hand, originate from supersymmetric gauge theories, which Matthias mentioned, in various space-time dimensions, 2, 4, 6, and 8. On the other hand, they describe the growth of discrete structures, or growth or melting of crystals. And the crystals could be 1, 2, 3, or 4-dimensional. So on this picture, I have a 3-dimensional crystal, and its boundary is a 2-dimensional random surface of some kind. So some of these models have some common features with the very exciting and still actively studied diffusion linear aggregation model. I don't claim that the model which will have 3-dimensional boundary geometry will quantize 3-dimensional Euclidean gravity, but it appears that it actually might teach us something about the 11-dimensional supergravity, or something which goes beyond that. So the idea to build a random geometry model in d dimensions is to start from some local growth model in 1 dimension higher. So, for example, start with the simplest mathematical, in quote marks, problem counting natural numbers. So these are objects without any structure. That's like a 1-dimensional crystal. So you just stack these objects on top of each other. The boundary of that is not interesting. It's just one thing. But once you start adding some structure, namely, for example, you can look at the same integers, but now you can try to partition these integers as sums of integers. So think of elementary blocks and then some kind of bound states. So then to represent the partition of an integer as a sum, so to represent the bound state as a result of combining some elementary ingredients, we will see now a two-dimensional structure, commonly known as a Young diagram, and the boundary of that structure is now a curve, and the curve is kind of wiggly. So mathematically, partitions, the ordinary partitions are, well, they're described as a diagram in 2 dimensions, or as a collection of sequence of numbers, which is not non-decreasing. Now, to make a partition physically, you take a pile of bricks and throw them into a cart. And so you throw them one by one, kind of randomly, and then let gravity slide the bricks all the way down. But of course, there are some ambiguities, and so you may arrive at different shapes of the pile in the end. So here, for example, I drew a partition 2, 1, and this is a partition 2, 1, 1, and this is a partition 3, 1. So some of these partitions are, of course, related by mirror reflection, but these are different partitions. So you can organize these structures by, so if you have bigger and bigger piles of bricks into a graph, which shows how you can get from one partition to another. And that's the growth model I was referring to. So first you start with nothing, you add one brick, and there is only one way to do this. But then the second brick, you can throw either on top of that or to the right of it, and so on. And so there are, as you go down this graph, you have more and more ways of arriving at a given vertex, starting from the top left corner. So you can assign a probability to a given partition by counting the number of paths connecting it with nothing. For example, the partition 2, 1, 1 has 3 paths connecting it to the empty partition, and then taking a square and then normalizing. So taking a square means that the probability of a given partition is proportional to the number of ways it can be built out of nothing times the number of ways it can be reduced to nothing. So so it's like in quantum mechanics when the probability is the absolute value squared of the amplitude. And the amplitude is the sum of a paths. So this way of assigning probability to a partition represents the bricks I was talking to as quantum bricks. And this is known in mathematics as the so-called Plancherel measure. It has a meaning in representation theory of symmetric groups. And this number of paths can be computed explicitly as a function of the geometry of the partition, essentially as an inverse product squared of the hook length of the cells in the Young diagram. So, for example, for this partition 3, 1, so we have 4 cells. Each cell has a hook number. So this one has hook length 1. This one has hook length 2. This one has hook length 4, and this one has hook length 1. And so this, when we take the square and put it in the denominator, we'll get 1/64. So that's not a very probable partition. Remarkably, this probability measure, which comes from representation theory, also was found later, much later, like 40 years later, 30 years later, in a completely different realm of mathematical physics, in the studies of supersymmetric gauge theory. So in gauge theory, we study the dynamics of connections in 4 space-time dimensions, together with some additional fields, and the supersymmetric theory with n = 2 supersymmetry has has a pair of Weyl fermions and a pair of scalars, all in a joint representation. And there are some transformations, symmetry transformations, which map bosons to fermions, hence they're called supersymmetry. Now, in computing the integral, the path integral over such fields, the configurations which preserve supersymmetry, so for those for which the right-hand side of this transformation is equal to 0, play a special role because the integral which we're evaluating can be evaluated exactly by saddle point approximation. And so with various regularizations and precisions, the invariant field configurations turn out to be labeled by partitions or collections of partitions. And the measure, so the contribution of a given partition will be of the form of the Plancherel measure or some generalization. So more precisely, there are several parameters one can introduce to make to measure depend not only on the to make it slightly asymmetric. So the Hooke measure was kind of invariant under the reflections, but the gauge theory makes natural a more general measure which is slightly inhomogeneous, which in the simplest case of rank 1 theory was also, of course, found by mathematicians in the studies of the so-called Jack symmetric functions, Jack polynomials. So at any rate, the supersymmetric gauge theory, at least in a certain restricted sector, becomes a model of random partitions, random piecewise linear geometries. So for gauge theory, with the gauge group U3, for example, in the slide, the objects which grow are 3 partitions, which grow at the corners of a kind of a piecewise linear room. And there is a probability measure on such configurations, which can be written as essentially as a Boltzmann measure, Boltzmann weight, or Gibbs measure corresponding to an energy of the configuration represented by the boundary of this collection of Young diagrams, which corresponds to some kind of interaction of wiggles in this boundary. And there are 2 kinds of wiggles, so the convex and concave, and they act as positive and negative charges. So this model of random partitions, which comes from gauge theory, is a model of a one-dimensional plasma of charges of both signs with a tricky potential, interaction potential. This potential is actually logarithmic at short distances, so it looks like a Coulomb interaction, but it's flattens at large distances. Now, in the limit, when one sends this parameters epsilon 1, epsilon 2, which I introduced to regularize the theory, when one removes this regularization, the sum of the random partitions is actually dominated by essentially smooth geometry. And so that's an example of the geometry emerging from a discrete model. In this case, the geometry is one-dimensional. It's a curve. So it's a limit shape. It's a curve. It's actually it's piecewise differentiable. It has some flat pieces, and then has some splines which connect flat pieces. So it looks like a boundary of a crystal in 2 dimensions. Now, if you don't take this limit epsilon 1, epsilon 2 to 0, then you discover what Matthias mentioned, that the sum of partitions happens to have an unexpected first relation to mathematics and physics in 2 dimensions. Namely, it happens to be a conformal block of a 2-dimensional current algebra or W algebra, something which comes from 2-dimensional conformal field theory, solution of Knizhik-Zamolodchikov equation or Belavin-Polyakov-Zamolodchikov equation, except that it's a more general solution of those equations than those found in the studies of two-dimensional rational conformal field theories, namely the objects which come from 4 dimensions allow complete analytic continuation in all parameters, something which people used in the 80s in the studies of two-dimensional theories, but I would say could not really understand why this was happening. Now, this beauty definitely begs to be generalized to high dimensions, and it turns out that one can add additional dimensions to the story and study the corresponding partition functions. And one of the applications is the test of some of the very interesting predictions of string theory evolution of mid-90s. For example, without going into detail, the sum of the so-called D0 branes in string theory, so it's these are some kind of particles which interact via whose interactions can be described in some approximation by matrix supermatic quantum mechanics. And the prediction of string theory was that once one sums over the number of those branes, so one considers some kind of a grand canonical ensemble of these quantum mechanical systems, one should see emerging additional dimension of the theory. So this could be a dimension of 11-dimensional supergravity if one starts in 10 dimensions, or it could be the emergence of a 6-dimensional theory if one starts in 5 dimensions. So, for example, the slight generalization of a partition function, which I described before, the so-called Q analog of it, which it corresponds to study quantum mechanics on the modular space of instantons as opposed to just integrals over the instanton modular spaces. One finds a partition function which, after the resummation, can be cast in the form of a partition function of Witten index of a high-dimensional theory. And with the further analysis, that theory happens to coincide with the minimal 6-dimensional 2,0 multiplet. I apologize for the typo. I was recently taught that we use 0,2 for 2-dimensional supersymmetry and 2,0 for 6-dimensional supersymmetry. So this should be a 2,0 supersymmetry. It's a so-called tensor multiplet. It's a peculiar set of fields which live in 6 dimensions, which contain scalars, fermions, but also a 2-form, which is peculiar in that its field strength is self-dual. So it's a 6-dimensional analog of a chiral boson in 2 dimensions. So its partition function can be computed. It's a free field. It's a set of free fields, even though it's 6 dimensions, but it's a set of free fields, so it can be computed, and it happens to coincide with something which was computed by hard computation involving interacting fields in 4+1 dimensions. So armed with this success, one can try to go even higher and study the so-called plane partitions. So instead of 2-dimensional Young diagrams, one would be describing 3-dimensional Young diagrams, collections of cubes. So this is a projection of a collection of cubes from 3 dimensions onto a plane. So just like the ordinary partitions were the sequences of integers which were not decreasing, the plane partitions are sequences of partitions which are non-decreasing, in the sense that they contain the next partition is contained in the previous one. And the notion of being contained is just a geometric notion, that the Young diagram is inside the other Young diagram. And the geometric object which we assign to it, of course, is the collection of cubes, something we all played with in the kindergarten. So you can view it as an array of partitions, or you can view it as a 2-dimensional array of numbers, the heights of the columns. So either way, you have a set of numbers. So now it's a plane partition in the sense that now we represent a number as a sum of integers which are organized in a planar structure, in a two-dimensional array. So such objects arise in the study of a non-commutative gauge theory in 6+1 dimensions. So there is some analog, non-trivial analog of the Plancherel measure, which one computes from gauge theory one-loop computations. And there is a string theory meaning to this computation. It counts the number of bound states of the zero branes in the presence of a D6 brane. And it turns out that the free energy of this system of plane partitions, that is the logarithm of the partition function, has the platistic form. So it can be viewed as the as a contribution of multiple windings over the temporal circle of a single particle object, and the partition function of the single particle object turns out to be with an index of an 11-dimensional graviton, supergraviton. So somehow we start with counting cubes at something which we can do in the laboratory because it's ordinary three-dimensional cubes. You just stack them at the corner of the room. The probability of a given configuration of cubes depends on the shape of this configuration, and so there are parameters. There are three parameters: Q1, Q2, Q3, which know about the three-dimensional extensions of this three-dimensional Young diagram. And there is one more parameter, P, which is the fugacity, which is just the number of cubes. So at the outset, these are parameters of completely different nature, yet when you sum everything up, you discover an unexpected symmetry which permutes 5 parameters, which you can build out of these 4 parameters, so that there are dual partition functions, dual systems which have the same partition function. So it is something like Kramers-Vanier duality of the Ising model, but maybe it's more like the symmetry of a Potts model. Anyway, so the symmetry which the original model had just from the geometry, the symmetry of permutations of 3 axes gets enhanced to the symmetry of permutations of 5 axes. And these are 5 axes of a complex 5-dimensional space, which is the 10-dimensional space of 11-dimensional supergravity. So there is some understanding of why this had to be true to some extent from string dualities, but this is actually an exact computation, and so it was a conjecture I made in 2004, which was proven rigorously by Andrei Okounkov a couple of years ago. So the lesson from this is that it seems natural and interesting to study the arrangements of cubes or cuboids in various dimensions, and so we can visualize. So we don't have to have a d-dimensional imagination to do that. It's enough to have d-1 dimensional imagination because we can project. So the next step would be to go to 4-dimensional Young diagrams. And so if we visualize 4-dimensional Young diagram, we project the 4-dimensional space to the 3-dimensional space along the 1, 1, 1, 1 axis, just like we do the projection of a 3-dimensional space onto a plane. So if we project along the axis 1, 1, 1, R3 to R2, a collection of cubes, that will give us a tessellation of R2 by rhombi of 3 kinds, 3 orientations. So that's in this picture. So this is you see 3 types of rhombi which fill the whole space. So if we do that now in 4 dimensions, we'll get a tessellation of a 3-dimensional Euclidean space by squashed cubes, and we will have 4 types of those. So if we start with 4-dimensional Young diagrams, which I will introduce, we'll end up dealing with random 3-dimensional geometries. So that's we're getting closer to 3-dimensional gravity. Now, it turns out that the count of the 4-dimensional Young diagrams is something which mathematicians have thought about before. These are called solid partitions. They are solid partitions because now you arrange the numbers whose sum gives a given number into a 3-dimensional structure. So the famous attempt to write a formula for the number of such partitions was due to Percy McMahon in 1916. So he generalized the formula of Euler, who wrote a generating function for the count of the ordinary partitions, which is now, of course, it's elementary exercise. So he first found the formula for the count of plane partitions. That's and so it looks like a clever generalization of Euler formula where the factors in the Euler product are raised to the power n. So McMahon conjectured that if you now go one step further in dimension, if you go to 4 dimensions, then this factor should become just the next binomial coefficient. And so if you do this count by hand, and if you substitute it into McMahon formula, the result which you get will be correct for the first 5 for solid partitions of the first 5 integers, and for the 6 it will be off by 1. So it will be his formula gives 141 instead of 140, which is the correct number. So it's a small mistake, but unfortunately it's a mistake. So McMahon's formula is not correct. So it is actually, 100 years later, it is not known whether the formula for the simple count of solid partitions exists. There are supercomputer experiments which show that the asymptotics of that formula is captured by McMahon, but the deviations are kind of random. So this is probably reminiscent of the story of zeros of a zeta function, or the distribution of prime numbers. So there is some noise over some average growth. So McMahon gives the average growth, but to describe the noise precisely seems to be out of reach at the moment. But the supersymmetric count of solid partitions is something else, because we are going to give the measure on a set of partitions which will depend on additional parameters. Because for us, these 4-dimensional Young diagrams arise as instanton configurations in super-Young-Mills theory, non-commutatively deformed super-Young-Mills theory on R8 cross S1. And so that gives what I call the magnificent 4 partition function. It depends on various parameters, which are, some of which have to do with the geometry, Q1, Q2, Q3, Q4. There is one parameter, P, which is a fugacity as before. There are some additional coloring parameters. The parameters Q1, Q2, Q3, Q4 actually are constrained for supersymmetry reasons. So actually there are only 3 independent parameters, just like we had for the count of plane partitions. But there is one more parameter mu, which somehow, which is it's some sort of mass parameter. It turns out that this additional parameter, when you specify it to special values, you will recover this measure on solid partitions would get localized on plane partitions. So the solid partitions will not be allowed to grow in one of the 4 dimensions. But for general value of mu, they're completely 4-dimensional. So there is not yet a theorem for what the partition function of that model is, but there is a conjecture, and the conjecture is that it is again is given by some kind of free field partition function with even greater number of free fields, free bosons and fermions, and that formula has been checked now beyond the critical case of 6 instantons, which was the stumbling block for McMahon's formula. So together with my postdoc, we checked it up to 16 instantons, and 16 is important because 16 is 2 to the 4th, and it means that you can build cube of size 2, and because of the relation Q1, Q2, Q3, Q4 equals to 1, it could be a dangerous contribution of the building blocks which are extended along the great diagonal. But it works, and then Rubik Pogosyan told me that he managed to check it even for 17 instantons. So there's no doubt that this formula is correct now. But what does it mean is a complete mystery, because it generalizes the partition function of 11-dimensional supergravity. So what is the minimal number of space-time dimensions which would realize, which would fit this linearized set of fields is not known. So perhaps we should go beyond 11 dimensions, and that means that we should abandon Poincare supersymmetry as a kind of a natural symmetry of a typical background. So with that, I would like to thank you. I hope I convinced you that the study of instantons in the various incarnations is an interesting story. And if there are questions, I can show a few more slides. Thank you.
Thank you very much for these beautiful lectures. Are there questions here from the audience? So I had a small question. So this McMahon formula always seemed to overcount. Is this true?
You mean let's go back. That's a good question. Well, yes, it seems that, yes, it did. It seems that it overcounts, but I don't know whether it's always true, because it should give the right asymptotic. So probably at some point it should undercount, because if it's wrong, but it's a noise, then it should go up and down. So, but it's not enough to see the first. So what I wrote is for the first 17 numbers. But I think people now have checked for hundreds, and so probably it sometimes it's undershoots, sometimes it's overshoots.
So you have a formula that in some sense generalizes it, because you have these additional parameters, and then I guess some limiting value of these parameters should give you the correct counting function. But I assume you can't analytically take this limit, or what is?
Okay, so I thank you. Unfortunately, not. Well. First, it's not obvious how to set the parameters to get the homogeneous measure, but if these computer tests are telling us the true feature that the McMahon formula gives the right asymptotics, then it would mean that it would not be possible to specify the parameters to give the counting, because my partition function actually asymptotically behaves as the count of plane partitions. So even though this is a partition function of solid partitions, and so they are fully four-dimensional, but it turns out that this measure is such that because of some kind of oscillations, most of the time these partitions, they tend to sit near the coordinate hyperplanes. So they are mostly three-dimensional. So the asymptotic growth of this formula is that of it's some complex power of the McMahon function of three-dimensional partitions.
But you say it still manages to reproduce correctly the number up to 17. So how does that? Not the
number. No. Okay. I should. Okay. Let me say it again. So this partition function on the left, it's a sum over the solid partitions where each partition has a probability which is given by some complicated formula, which depends on Q1, Q2, Q3, Q4. Whereas in the old-fashioned way of counting solid partitions, you just count them without any additional weight.
I see. So you're saying you produce the sum of all the partitions together with the probability, i.e. the number squared of the ways you can build it up from the empty partition.
That was in 2 dimensions. So this is a kind of a generalization of that, right? It's
so your probability is not just the number of ways to make it from the empty partition.
No. This is it's more complicated. It has this. Okay, let me go back to the 2-dimensional case. It has some surface tension. So it's so the probability of a partition even in 3 dimensions in 4 dimensions, it would be given by some kind of a double integral over the boundary of interaction energies between the wiggles of the now 3-dimensional boundary. So those cuboids attract or repel each other, and so that produces some kind of energy which enters the Boltzmann weight. And I don't know how to make this energy disappear. So to go back to the just count of partitions without any structure would mean that you tune the parameters so that there is no interaction energy, and I don't know how to do that in 4 dimensions.
You mean there's
in 3 dimensions? In 3 dimensions, we can do that, and so that's the ordinary McMahon formula.
But so there's no combinatorical formula for this probability that you can say. You can't describe it in terms of a combinatorical description of this.
Yes, you can describe it. It's just a bit involved. Yes, you can describe it. It's some product over the four pairs of solid partitions, pairs of cubes inside this solid partition, some function of the distance between these cubes. No, it's explicit. It's involved, but explicit. So this is what we're checking on the computer when we do computer checks. That this free field formula, which emerges out of this complicated measure, works. So that's the statement.
I see. Are there any other questions from the audience here or online?